have 693 slides.
Okay. You professor? Right, and he's obviously an expert in this field, and he's graciously agreed to talk to us. Dr. Ramakrishna is a fellow IIT alumni from IIT Madras, Chennai.
Yes!
Oh, come on, come on! Oh, that's why all the IITM people showed up today. Okay. Anyway, and he's got his master's and PhD from MIT. Okay, what else did I want to emphasize? He started his career as a McKinsey consultant.
Sorry about that.
So, yeah. Do you still admit to it? Okay.
Yeah. I mean, after the John Oliver episode came out, not so much.
Right. Went on to be an entrepreneur, started a couple of companies which exited successfully to Oracle, Salesforce. He's been an executive in those companies. And now he's a professor at MIT Sloan and focusing, I believe, on this area and the business aspects of it. So I won't take too much of the time. Just get Dr. Ramakrishna to get started.
Great. Thank you. Thank you for the kind intro, Surya. Appreciate it. And thanks for inviting me to speak at this forum. It's great to, sort of reconvene with folks from IIT, as always, and others, all the folks who are interested and who are here. First of all, thanks for taking time out on a Saturday morning to be here. I know some of you drove like 45 minutes to an hour to get here, and I particularly appreciate that. So I do have roughly 700 slides, but I'm going to go through them quite fast, which means that if you don't pay attention for 10 seconds, you won't make it.
This is like Game of Thrones.
Yeah, so you have to pay super attention. But I actually mean it only half joking, in the sense that I'm going to cover a lot of ground because I didn't want to make any assumptions about what people know about the space before they walk in here today. So I'm going to start from the basics, and then I'm going to go up to the most recent emerging capabilities, all in this span of 75 minutes. So we'll cover a lot of ground. If you have a burning question, just interrupt me. But if you think it can wait, we'll have ample time for Q&A at the very end. And I'm not going to get very technical. Obviously, this is probably a somewhat technical crowd, but not everybody is technical. So I'm going to keep it non-technical. Doesn't necessarily mean the concepts are easy, right? So that's why I think paying attention is really important. And for those of you for whom this material is very obvious because you've seen it before or you're very familiar with it, just fake interest so that I don't get demotivated. Okay? All right. Okay, let's get going. So this is going to be the agenda. I'm going to spend a few minutes on sort of giving everyone an orientation for all these phrases that we are hearing, right? Machine learning, deep learning, Gen AI, so on and so forth. What the heck do these things actually mean and how are they different? Because everybody out there has taken the phrase AI and attached it to whatever they are doing, right? Indiscriminately, in my opinion. So it's good to know what's what. And then we'll actually switch gears and do a deep dive into LLMs, large language models, how they were built, and then if you want to build an application with it, if you want to actually use it in a business setting, how do you actually go about building applications? And then how do you do so very carefully, because LLMs have lots of very interesting risks that are not always talked about as much as their potential in the media. And then I'll have some recommendations for how you safely use them in the enterprise. And then we'll spend a few minutes on emerging capabilities, because this space is moving at an incredible speed. In fact, people like me who work in the space, we are kind of very stressed constantly, because at any point in time in a presentation, I have no idea if what I'm actually saying that day has already become obsolete the previous night. And I'm not saying this sort of lightly. It's a really big problem for all of us to keep up with what's going on. So I do spend an inordinate amount of time trying to stay on top of what's going on. So we'll see if that works. Okay, so the field of AI originated in 1956. Sadly, it originated in Dartmouth, not at MIT. And this is the group of people who got together and coined the field, coined the phrase artificial intelligence. At least MIT was well represented. That's Marvin Minsky, AI pioneer. He founded the MIT AI lab. There is John McCarthy, who invented Lisp, and who later sadly went on to Stanford. And then this is Claude Shannon, who invented information theory, right? Basically a bunch of your, average brainiacs. They get together at Dartmouth, coin the field, and then essentially they declare by kind of mid to late fall, we probably would have cracked the key problems in this space. In 1956. Okay? So obviously that doesn't happen. But over the last roughly 7 decades since the founding of AI, it has gone through what I think are 3 seminal breakthroughs. Okay? So there was a traditional approach to doing AI, and then there was a key breakthrough called ML, and then deep learning, and then Gen AI. And each breakthrough essentially came about to solve a shortcoming of the previous version of AI. Okay? So now what is AI? We can actually spend like 3 days talking about what is AI, but let's not do that. So I'm going to have an informal definition, which is that can we give computers the ability to do things that traditionally only humans can do? Right? Cognitive tasks, thinking tasks, and the like. And so if you set that as the goal, perhaps the most commonsensical way to approach that goal is to say, hey, why don't we just ask, let's say we have a task that we want the computer to do, why don't we collect a bunch of humans who are really good at doing the task, we'll sit down with them, ask them to explain to us how exactly they do the task, we will try to capture and codify these things in the form of if-then rules, and then once we have if-then rules, we are in great shape because we can just directly put it into the computer. Okay, that was a traditional approach. It sort of meets the common sense test as something that any of us might have come up with, right? So that's how it works, right? You have an input, a bunch of if-then rules, and you have the output. So let's say that we use this approach to build a chair and stool detector. Okay? So the task we have is very simple. I'm going to give you a picture of some furniture, and I want your AI system to look at this picture and say, hey, that's a chair or a stool, or neither. That's it. Very simple task. So we consult human experts, i.e. ourselves, and we say, well, you know, if it has 4 legs and a base to sit on, it's probably a chair or a stool. That sounds pretty good, right? So this is version 1.2 of your system, and you deploy it, okay? And then sure enough, you run into this exam, okay? And this is not a chair or a stool. It turns out it's a side table, okay? So you're like, that's a corner case, right? Or as they say in the industry, it's a failure mode of your system. So you want to go back and make your system better to handle stuff like this. So you modify your rule to say, if it has 4 legs and a base and can seat just 1 person, it's a chair or a stool. So you deploy the system, it seems to work pretty well, and then boom, you run into this corner case. Okay? So the previous thing was a table, like a dining table, a low dining table. This one is like actually a corner table or a side table. Okay, so that doesn't work. So you're like, oh crap, this thing doesn't work. You get the idea. This process is never ending. It's long, tedious, and error prone. Okay? And for this reason, the success of the traditional approach of doing the asking humans and figuring out these rules was successful in only a few limited areas. Okay? Now, it's actually very interesting to step back and ask ourselves, why did it not work? Okay? And the reason it didn't work is actually very subtle, yet obvious. Okay? It's one of those slippery things. So, first of all, Polanyi's paradox. We know more than we can tell. So, if I ask you, when I gave you a picture, Rupesh, how did you actually figure out if it's a chair or a stool? Rupesh, you can tell me a whole bunch of very plausible sounding reasons why you did that. But the reality is you don't know. Right? First of all, sometimes we can't tell how we do certain things, and even when we can tell how we do those things, we are actually bullshitting very often. Okay? Because the way our brain works and the way we explain how our brain works, there's a big disconnect between the two. Because we are constantly making up stories, which may or may not correspond to reality. This comment has various implications on the political system, but we'll ignore that. But this is a fundamental reason. Okay, we know more than we can tell. We can't articulate stuff. The second thing is, even if we can break down a whole bunch of rules, thousands of rules, there is no guarantee it's going to cover everything that's going to happen in the real world. Right? There are going to be corner cases, you just can't provide for it. So there is no guarantee of generalization to the real world. So these two are the fundamental reasons why asking people how they do things and putting it in a computer just doesn't work. Okay? So this is the traditional approach to AI, and it's called GOFAI, good old-fashioned AI. You can actually Google it, GOFAI. Okay? So now, to address this problem, a very different approach was developed. Okay? This was the first breakthrough. So the idea, I still get goosebumps when I look at this idea, because it's so beautifully simple and elegant. So instead of telling the computer what to do, okay, why don't we simply collect a lot of examples of inputs and the right outputs, questions and answers, and why don't we have the computer just learn the relationship between the inputs and outputs using statistical techniques, okay? Don't collect understanding from human beings, collect examples. I think we can all agree that collecting examples is a lot easier than collecting understanding, right? So this is machine learning. So AI is this big field, and a small part of that field is called machine learning, okay? And machine learning is nothing more than learn from input-output examples using statistical techniques. Okay? Alright, that's machine learning. Now, machine learning has a bunch of other stuff. Unsupervised learning, reinforcement learning, and so on and so forth. I'm just ignoring all of that because the lion's share of today's activity in machine learning is something called supervised learning, which is learning from input-output examples. Okay? Alright, so let's say you want to build an AI system to predict cardiac risk from patient data. So, previously, you would talk to cardiologists, extract rules from them and put them into the computer, but we know that doesn't work. So what you do instead is you collect input-output data from an electronic health record system. So maybe you collect data like this, right? You're like, okay, you collect data on patients on variables that you think are relevant. So for example, clearly the age probably matters, whether they are a smoker matters, how much exercise they do matters, cholesterol matters, and so on and so forth. You collect all these things when they come in. And then, maybe a year later, you check whether that patient has had a cardiac arrest in the preceding year. That's your matching output. So you have input and you have matching output. Match to that input. Okay? You take all this data, and once you have this data, you're in machine learning territory. Okay? Building a system is basically trivial. So you just take these inputs, take the matching outputs, and send it through and build a prediction model literally in a matter of minutes. Okay? And there are numerous ways to build these models, right? How many of you here have done linear regression? Congratulations, you have done machine learning. I'm not kidding. Okay? Linear regression is a statistical technique to map inputs to outputs, therefore it is machine learning. So, but there are many other things you can do. Classification trees, support vector machines, random forests, the list goes on. Okay? And it's a vast area and it continues to expand. So, this is machine learning and it has had incredible impact on the world. Like massive impact worldwide in all kinds of areas. There's many of the startups that have been involved in, we all basically were doing machine learning, but to solve a whole bunch of problems. But it has one important limitation, one Achilles heel. Can anyone guess what the Achilles heel is? Should be what?
The variables.
Yeah.
Or the inputs and the correlation. That's again human.
No, it's not. Because if you actually, just to go here, this data just came from an electronic health record system.
Right. The data points that you say you're collecting, you're limited to say those are the only attributes that impact.
Correct.
You don't know what others do.
There could be others, but that's not a limitation of the model itself. It's a limitation of the fact that you could not give it better data. Clearly, if you gave it better data, the same model will do better, right? So the key thing here is not so much whether you were able to give it better data. The key limitation is something slightly different. You want to take a
number of parameters, how many x1, x2, x3, so on you put, that you don't know, sometimes it becomes very large.
It could be large. Maybe you have too many columns and not enough rows. That's a limitation. But there are ways to get around the limitation too. Yeah.
It's not generalized very well if you put in too much data and too many variables.
Actually, if you give it a lot of rows, it gets better and better. Yeah.
It's a pure correlation, but it doesn't tell you what.
Right, there's no causation.
Yeah.
I agree. But I'm not trying to be causal here, just to be clear. I only want to be correlational, but I just want to be better at correlation. Right? Great limitation, and in fact that limitation exists to this current day with all AI systems. But my ask is a little more modest. Durya, you had it up.
Yeah, it's whatever statistical model it has used to do the correlation in the past, it's now using to project the future. But you're not exactly sure if that's the right statistical model.
Right, what you're saying is that maybe the data you use to build the model doesn't correspond to the real world in which the model is going to be deployed. Maybe the world has changed. and maybe it's not going to work. That's a limitation of any model built on historical
No,
data.
I think what I was trying to say is the way it's modeling that data may not accurately reflect.
But what you can do, that's a good point. What we can do is instead of using simple things like linear regression, we can use a deep neural network.
Sure.
We can use
You're
much
covering
more
all of them then.
we can use, assume we can have a very complicated model.
Yeah.
Okay?
There's a feedback.
You should have a large number of data and compare with the parameters which you choose. That also is another point.
So you folks are all fishing in one small pond.
It's a
Yeah.
feedback mixed model.
There is no, you can have feedback mechanisms with any model. You can actually predict it, you can then find the right answer, and then you can collect it, and then you can retrain the model on the right answer. So I'm going to move on, okay? I was about to call on IP because I always call on students who are looking at their phones.
He's very focused.
There you go. You got it. You got it.
Hi. All right. So, okay. So the limitation, and I know that my question was sort of vague, and so your answers are not incorrect. Right? Those are all limitations, but they are not limitations of machine learning as an approach. That's what I'm pointing out. So it turns out it's really good only if the data is structured. What do I mean by structure? What I mean by structured is any time the input data can be sort of numericalized and stuck into like the rows and columns of a spreadsheet, machine learning can handle it. You know, it can handle it better if you have lots of data, maybe not so well if it doesn't have lots of data. Maybe it can handle it better if it's a complex model, not so much if it's a less complex model. Right, so on and so forth. But the fundamental limitation, the fundamental requirement is the data has to be numericalized. By numericalized, I mean either it's already numerical, like age, or you can take something which on the surface doesn't look numerical, like family history of heart disease, and then you can convert it to a number very easily. So for example, in this case,
like a binary, 1, 0.
you nailed it, buddy.
1 would be yes, 0 would be no.
Yes, exactly. So family history of heart disease, yes or no maps to 1 and 0. Okay, so it's either numerical or can be made into a number pretty easily. Okay, that is the key requirement. Now, if you have something like this, if you have an image, that's my puppy buddy. So, if you have an image like this, if you have natural language tables and so on, you don't know where to start. That's the problem. If you have unstructured data, machine learning comes to a grinding halt because it expects essentially a spreadsheet is an input. So the reason why unstructured data is so hard for machine learning is that if you look at a picture like this, the way it's actually represented digitally is basically 3 tables of numbers. So any colored image has what's called 3 channels, red, green, and blue. And let's say you take this particular corner here. That corner is a pixel. And what is a pixel? It's just a bunch of numbers, right? And in particular, it's a bunch of 3 numbers. The first number tells you how much redness is there in that location. The second thing tells you how much greenness and then how much blueness. Because any color can obviously be constructed by mixing reds, greens, and blues the right way, right? So these 3 numbers, 251, 186, and 147, tell you the color of this location. Okay? Now, if that location is green, the way it looks, but if the underlying picture is not a puppy, but a forest, guess what? The number is going to be the same. Right? As long as there is green in that location, regardless of the underlying reality of what the picture captures, the numbers don't change. Forest, same thing. Puppy, same thing. Everything, same thing. So, therefore, there is no connection between the numbers and the underlying reality of what the image is capturing. So, given that, how can any model do anything with this? Now, I'm just giving you a bunch of numbers, 256, 353, I'm like, figure out if it's a puppy or not. I have no idea. So, that's the fundamental problem. Raw data, the raw version of unstructured data has no intrinsic meaning. In contrast, if you look at something like blood pressure, a whole bunch of human beings over centuries have defined the notion of blood pressure. They have defined the notion of how to measure blood pressure. They have measured it. So the innocent act of having a column like blood pressure here, just think about it. It embodies decades and decades of human ingenuity to figure that out. And they have deemed it as something worth measuring. So basically, when we are working with structured data, we humans, with our brain power, or doing the hard work of creating structure, imbuing data with structure, and sticking it to a spreadsheet. That's why it works. Because we have done the heavy lifting before we gave the job to machine learning. Okay, so with unstructured data, well, we can't do that anymore. Okay, so to use machine learning on unstructured data, we have to manually structure. Okay, in the olden days. Olden days as in like pre-2014. So, so what people would do is, let's say that you wanted to build a system which can look at pictures of birds and then figure out which species of bird it is. Okay, so you carry a whole bunch of pictures. And then since you can't use the picture as is with machine learning, what you basically want to do is you want to take all these pictures and basically create a spreadsheet from them. And so you may decide, and this is where your domain knowledge comes in, you may decide that measuring the beak length, the wingspan, the primary color, and so on are all important things for us to know to figure out what species of bird it is. And therefore, you can take each picture and literally measure the beak length, the wingspan, the color, and so on, and then you put it in. Now, once you go from here to this spreadsheet, life is good because you can apply machine learning to it. Make sense?
Yep.
Okay, good. All right. So, but structuring the data requires massive human effort, and it's a massive human bottleneck. Okay, and this bottleneck sharply limited the reach of machine learning because you could only use it effortlessly where structured data is already available. So, all right, to address this problem, you needed a second breakthrough was needed, and that is deep learning. Okay, so deep learning is just a particular kind of machine learning, and you can predict at this point what deep learning can do that machine learning can't. What can it do?
Take unstructured data.
Correct. It can work. It can handle unstructured data with no human intervention in the beginning. So this is the fundamental reason why AI is so popular, right? It doesn't make for great press releases, but this is the fundamental reason. So yeah, so deep learning can handle unstructured input data. So it can handle these pictures, it can handle text, obviously it can handle traditional structured data as well. It can handle anything as an input, and it can do so without manual upfront pre-processing. So this demolishes the human bottleneck for using machine learning with unstructured data, which means you get here was that the same underlying approach, deep learning, then they applied it to speech recognition, it crushed it. Natural language understanding, it crushed it. So you take a generic algorithm, you apply it to 7 totally different areas, and it becomes the world leader in all 7 areas. That's not a fluke. There is something deep and seminal going on for that to be true, right? That's exactly what happened. So now, what is deep learning? First of all, deep learning is actually a twist on an old idea, first of all. So there is a technology, a machine learning approach called neural networks, and you saw me, I had it on that list in the previous slides. So neural networks we knew were always theoretically very capable of doing great things, but you could never get them to practically do, right? And it turns out, with a few algorithmic ideas and an amazing amount of data, thanks to social media, e-commerce, basically the digitization of activity, and then a whole bunch of compute power, thanks to GPUs, right, parallel processing hardware. These 3 factors came together in a perfect storm, and then they took these 3 things, applied it to the old technology called neural networks, and all hell broke loose. That's literally what happened. And in my opinion, I think it's possible. The math was actually the least contribution, made the least contribution. I think the data and the compute was actually the more important contributions to make this happen. And between the two, maybe the parallel processing hardware perhaps is like the first among equals in terms of its importance, and that's why NVIDIA crossed 3 trillion market cap this past week. Right? Because they are the sole purveyors of industry-grade GPUs at this point. Okay, so that's what it is. Now, what is the key idea behind deep learning? Right? The key idea is actually beautiful and powerful. So, take a good old regression model that many of you have known and loved, or at least known. So you take, in regression, you take the input, and then you basically do a linear function of the input, and then you just pop it out as an output. That's it. Input comes in, a linear function out pops out, right? So maybe you have x1 and x2, your regression model says, well, the right model is 20 plus 2x1 plus 3x2. That's it, you're done. In deep learning, what you do is you take the input and then you transform it a whole bunch of times. And when you're done transforming, you still run it through linear regression. And all pops out. So the secret sauce is all in these transformations. Okay? And by the way, when you repeatedly transform an input before you run regression, it's called a neural network. Okay? And each of these transformations, they get stacked in layers, right? Each one is called a layer. And by now, I think you can guess that deep learning is just neural networks with lots and lots and lots and lots of these intermediate transformations. Okay? This is an example of a neural network which by modern standards is sort of quaint and small. But when it came out, whatever, 10 years ago, it was like a hot thing. Right? So this is an example of a neural network. You can see here, the input comes in, it goes through a whole bunch of transformations, and then at the very end, what you don't see here is the fact that this little thing here is actually linear regression. And then out pops that. Okay? Now, the depth or the number of layers, by the way, the reason it's called deep learning is because it just sounds a lot sexier than saying many-layer neural network. Right? So the people who came up with this stuff obviously were not just pure ivory tower academics, they had a feel for marketing. So, all right, so the depth actually matters because deeper networks, networks with more layers, will learn very complicated relationships between the input and the output. Because remember, the quest here is to learn relations from input to outputs, from inputs to outputs. Always, that is the quest. Okay? And the real world is very complicated. And so you better have the capacity to learn very complex things, very complex ways to go from the inputs to the outputs. And as it turns out, if you have lots of layers, it can learn extremely complicated things. And that's why, for example, you can give ChatGPT a little sentence and say, you know, write me a haiku about the Boston Red Sox in the style of a pirate. It's actually going to give you an answer. It's because the very complex mapping from that question to the output, right? But these things can handle it. And this is the secret sauce of why any of this stuff works, okay? The reason why this works is that given enough layers, a deep learning network very slowly learns very simple things in each layer, but each layer essentially is standing on the shoulders of giants. It's learning to transform whatever the previous layer has produced. So every layer is learning something very small and modest. But when you have 1,000 layers, 1,000 small learnings, each piggybacking on the previous learning, leads to something magical, right? So here, actually, they took a deep learning network and had it and fed it black and white photographs of human faces, okay? Black and white photographs of actually not human faces, sorry. Black and white photographs of human faces and non-faces, okay? And asked it to classify, is it picture, is it a human face or not a face, okay? And it did a very good job. It learned how to do that. Then they tried to figure out what exactly is each layer actually learning. Right? That's a very interesting question. Turns out, the very first layer, all it's doing is it's trying to figure out, are there any small lines in the image? Vertical lines, horizontal lines, diagonal lines, and things like that. Or faint gradations of the grayscale. The second layer, remember, the second layer only sees what the first layer gives it. And what the first layer gives is a bunch of lines, right? So the second layer learns to take two lines and say, oh, it's an edge. I'm seeing an edge in the picture. Or I'm seeing something, a shape like this in the picture, right? It's seeing these kinds of slightly higher level patterns. And then finally when you come to the later layers, it's actually able to recognize the face because the previous layers are already telling it, hey, here's a nose for you. Here is a circle, here's another circle. And it's saying, oh wait, if there are two circles in what I'm seeing, and if there's an edge like this, boom, it's a face. That's how it works. So each layer is learning something very simple because all the n-1 layers before it have done the heavy lifting. So this is the fundamental reason why deep learning works. The depth is everything. And GPT-3, for example, has 96 layers. Okay, so now what is the immediate sort of no-brainer application of this stuff? The things that we humans do quickly and effortlessly tends to be perceptual tasks, right? Seeing, classifying, hearing, recognizing, things like that. And what is the input to these particular tasks? It is just real-time video, right? It's just images, audio, and text. And with deep learning, we know that we can handle this sort of unstructured data super easily without any kind of pre-processing, which means that basically, I think Andrew Yang of Stanford said it well, if a typical person can do a task with less than 1 second of thought, we can automate it using AI either now or in the near future. That's it. I would make a small modification to this. I think if a person or even a trained human expert can do a task without extensive pondering, if it doesn't require a lot of judgment to do that, you can automate it now. We should all be very worried about some aspects of our jobs. But I'll talk about that a bit later. I don't want to completely screw up the vibe here. Okay.
We'll have one question.
Yeah, please.
Which is that even large amounts of data, the neural network has to be statistical by nature. It can't be analytical.
Correct.
Because there's too much complexity.
Correct. Yeah, basically it's doing pattern matching and correlational analysis effectively. But what is a shocker is that if you take correlation analysis and scale it up massively, magical things happen. That is the shocker. It's sort of like if I give you a picture book with images, right? You have these old picture books from when we were kids, right? You slowly flip the picture book, it looks like a movie, right? But suppose you slowly flip it. It looks like you're seeing one picture after another. But once the flipping rate exceeds a certain threshold, it looks like a movie. So this is a great example of a phase change, right? It's a phase transition happens. A series of stills is not a movie. So it's a good example of more is different, and that's exactly what we're seeing now. Okay. So what that means is that every sensor can be given the ability to detect, recognize, and classify whatever it's sensing. Okay. So for example, if you open your phone with your Face ID, the camera in the iPhone has a little deep learning module sitting behind it, and it's basically saying it's checking Rupesh, yes, no, that's it. Right? It's a binary classifier on your face. So it's basically working. So you have a camera sensor with a deep learning system behind it, which is classifying what it's sensing. Similarly with self-driving cars, right? A modern self-driving autonomous system has numerous deep learning systems running under the hood. Pedestrian detection, stop sign detection, zebra crossing detection. All these are different deep learning models, and they all work together to figure out what's going on in the image. Of course, it's being used for breast cancer detection and so on and so forth, mammograms, radiology, industrial inspection. Right? When a product rolls up the assembly line, before you would have people walk around the car, for instance, and say, okay, there is a dent, there is a scratch, stuff like that. No need to do that now. You just have cameras all around the car. You can you have a dent detector, a scratch detector, and so on and so forth. Okay. By the way, this is an example. I don't know if folks can see this little thing here. This is a mammogram, and this actually is an actual mammogram from one of my colleagues at MIT, who was diagnosed with breast cancer, and she works in this space. And turns out, she took the mammogram so she had a normal checkup. And then 3 years later, she had a checkup in which they said, there's a problem, we see something. So she took the 3-year-old picture, where the radiologist said everything is good, everything is clear. She ran it through the system, it picked it up.
Wow.
Yes. So those are all the examples that make me very optimistic overall about the positive impact of AI. Okay, so let's keep going. So what that means is that you can take any product or service that you have now, if it has any kind of sensors in it, you should immediately be thinking of attaching a deep learning system behind the sensor and making it smarter. So I just saw this cool example. Apparently it's the world's first smart binoculars, right? You take these binoculars, you look at something like a bird, it immediately tells you what the species is. It's just a sensor. You can classify it. So if you have products which have sensors and you're not doing it, you will not survive. Because the competition is doing it. Okay. Even things like smell. There's a deep learning system which can take your smell and classify it. Because fundamentally what happens is the smell gets transformed into a molecular representation, and once it's a molecular representation, it's unstructured data, boom, send it in. Okay, so deep learning has had huge impact already on a vast number of fields, and this is the landscape so far, right? We started with traditional AI, we talked about machine learning, and we talked about deep learning. Okay? Now, but we have been neglecting something conspicuously up to this point, and what we have been neglecting is the output. We have been very fixated on, okay, is it unstructured or unstructured data, what can it do? Now let's turn our attention to the output. So here, with deep learning, you can predict structured outputs very easily, right? So you can ask a deep learning system to say, well, here is the application for a loan applicant, all the data about them. Should we give them a loan, yes or no, right? That's a single number, no problem. Or you can have a supply chain application where you can say, for this product, given all the history of what we know about the product and the category of products, how many units will we sell in the Harvard Square store next week? 23 units. Single number, no problem. Now, or you can come up with a few numbers. So you can actually give it a picture and say, what is the probability that this piece of furniture is a chair, a stool, a sofa, or something else, right? 4 numbers, 4 probabilities. That's also very easy. Or you can give it, you can ask it to predict the GPS coordinates of a particular Uber. So when you have a few numbers, no problem, we can handle it. But what we could not do very easily is to actually generate beautiful images. We couldn't generate human-sounding coherent text. We couldn't do those things very easily. We could do it kind of, but not very well. Okay? And then a breakthrough happens. In 2017, something called the transformer was invented at Google. Okay? There are actually 2 Daisies in the machine. Ashish Vaswani and where is Vicky Parma. Okay? 2 Daisies in the team. Sadly, not promoted. Good for them though, very proud of them. So they invented the transformer, and that basically catalyzed the development of GenAI. Note that GenAI is just a small part of deep learning, okay? Because it uses a particular kind of deep learning. And so GenAI can produce unstructured outputs, right? You can give it a caption like generate a picture of a cute Labrador retriever, and you get my puppy. You can do that. You can go from image to text. You can go from this prompt to a beautiful picture. I'm sure you folks have all been playing around with DALL-E and so on and so forth. You can actually give it text, and you can actually create like a 1-minute video. You may have seen this before. So the prompt is in an ornate historical hall, a massive tidal wave peaks and begins to crash. 2 surfers seizing the moment skillfully navigate the wave. So. Pretty good, right? So, all from the single text prompt. Okay, and I did this yesterday because I was like, get it. So I went to a service called Suno, which just launched very recently, and I said, give me so you go from text to lyrics and music in one shot. A catchy Bollywood song about the Indian Institute of Technology. Okay, and here are the lyrics, okay? And I'm going to play the song.
You didn't say in Hindi or any other language.
No, I just said English. So Delhi, Mumbai, Chennai, counted for. Roorkee, Nagpur. IIT is where great minds glow. Engineering hearts beating free. Come on, give it up. Okay. You can check it. Suno.ai. SUNO. Okay. And this is my personal favorite. You can go from text. This text is basically an amino acid sequence, right? And you can go from text to the 3D structure of the protein. So whenever I think about AI and I'm sort of depressed about the impact on this and that and whatnot, and like deep fakes and whatever, I go back to AlphaFold 1 and AlphaFold 2 and I feel instantly better. And if you folks haven't spent time reading through the blog post and seeing the video, please do so, because it'll be very uplifting. It's a feat. It's an amazing feat. And we have sort of taken it for granted already. Yeah, permission.
Which model did you produce all this with the ChatGPT?
The previous one is Suno.ai.
Okay.
Yeah, Suno.ai.
And this one?
This one is actually the sources are all here. I took it from a tech. And by the way, AlphaFold, yeah. So just go to DeepMind, Google DeepMind, and search for AlphaFold. You'll find a whole bunch of blog posts, there are videos as well. and it also links to the Nature paper. But the way they did it, particularly AlphaFold 2, just incredible. Just to put it in perspective, it would take, once you figure out the amino acid sequence of a protein, it typically takes a PhD, a full PhD, to figure out the 3D structure. Okay, like 4 to 5 years. So these guys, they found the 3D structure of all 200 million proteins known at that point in time and put it on the public internet. 200 million times, let's say 5, a billion PhD years saved. It's like shocking.
How do you know it's right?
Sorry?
How do you know it's the right structure?
Okay, thank you, Rupesh. This was not a setup.
Did he page you?
Experiment, prediction. Experiment, prediction. Look at the match. So, but to answer your question, typically what happens is that the way they trained it on is that they had several hundred proteins, which they had, people had painstakingly, using X-ray crystallography, they had figured out the 3D structure, and that input-output pair was the training data. So that's, see, always, to get these models to do what they do, you need the right inputs and the matching outputs. And to do that may take a lot of effort. But you do it for 200 proteins, right? 200 times 4, right? 800 years. And then you save a billion years because your model does the rest of it. Okay. And of course, text to text. The reason why you're here with ChatGPT, right? Large language models. So it's 12:15, right?
Mm-hmm.
So I'm going behind schedule, so I'm going to speed up slightly. Actually, could I get a cup of water? Is it possible? So this is the landscape so far, folks, right? Whenever you're seeing things like AI, machine learning, and so on out there in the media, just remember, just map it to this picture, okay? So if it is using if-then rules, it's old AI. Machine learning from examples, but with structured inputs. If it uses unstructured inputs, it's deep learning. If it is doing unstructured outputs, it's Gen AI. So you might, if you folks are working in corporate and you have a vendor coming and saying, we have an AI system for this thing, and it turns out they're only using structured data, they probably are not using deep learning. So you can be the truth teller. You'll be respected, but perhaps unpopular, but that's your problem. All right. So now, with the rise of what I call multimodal models, which we'll talk about later, the circles inside Gen AI are actually merging already. Because a single model is no longer like text to text. It can do text, image, everything, and produce it. Like we saw with the lyrics, right? We gave it some text. It gave us both the lyrics and the music. All right. Now, deep learning, again, is the foundation on which everything is built. Without deep learning, there's no AI revolution. Which is why, actually, a few years ago, at MIT Sloan, I created this class called Hands-on Deep Learning, which teaches MBAs, often with not a big technical background, how to actually build deep learning models, because I think it's fundamental. And I'm glad to tell you that it's actually coming soon to OpenCourseWare, MIT OpenCourseWare. Okay, so, all right, we have just finished the first part of the agenda. So let's go to the second thing, how large language models work. So this is our quest. We want to build a model that can take in text and generate text, right? Now, like any good researcher, the first thing you want to do is simplify the problem, right? So what is the simplification of a problem that makes sense? Well, instead of building a model that can take in text and generate text, you just generate the next word. Because if you generate the next word, you can just keep on doing it again and again, right? So we'll just generate the next word. So given the cat sat on there, our goal is just literally generate that. So now, can we frame next word generation as a machine learning problem? Right? That's the key question, as a machine learning problem. Now, to put it in perspective, you may have seen these things where you give a machine learning system like a review of a movie, like the movie left me speechless, and then it tells you, okay, the sentiment is positive with some probability, negative with some probability, neutral with some other probability. This is a very basic classification system, right, which traditional machine learning can do. So here you take some text and classify it into 3 things, positive, negative, neutral. But what we want to do is predict the next word, so it is just a classification problem where you take in a bunch of text and you want to classify it into how many into one of how many output categories. But why? Like, why did you say that?
The possibilities.
You want to generate a vector with a probability.
Right, but how many categories should be there?
The vocabulary of the
Correct.
Of the language.
Exactly. That's exactly right. So what you want to do is the number of words in the dictionary. Because if you want to predict the next word, You don't have to come up, you don't have to dream up that word, you just have to pick it from a list, right? And so once you look at it this way, you suddenly realize generating text is just a traditional machine learning problem. Okay. So what we do is to train this model, remember for any machine learning model, what do? We need input-output examples. So we want to have things like the input can be the first part of a sentence, the output is the word that follows the first part. So for example, if the input is the cat sat on the output should be mat. Okay? If you have these input examples, you're in good shape. Now, where will we get these examples from? No problem, we'll scrape the internet. We'll scrape the internet. There are plenty of text on the internet. By the way, this approach of taking something and then creating an input-output from it automatically, like taking the cat sat on the mat and saying the cat sat on there is the input, the mat is the output. This is called self-supervised learning. Okay? For those who are sort of curious. Okay. Now OpenAI did exactly this. They scraped the internet and they assembled a data set of 30 billion sentences. Okay? And then they created input-output examples from each sentence. So if you take this sentence like the mission of the MIT Sloan School of Management, blah, 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 blah. So the input, first two words, off is the output. The mission off is the input, the is the output. Literally, you take each sentence fragment and take the next word, input, output, that's it. So from those 30 billion sentences, each sentence will actually give you lots of examples, like we have seen here. And once they did that, they essentially trained a transformer-based deep neural network on it to literally just predict the next word. Okay? Now, it took them months and millions of dollars to do this. Okay? But once they did that, they got GPT-3. So GPT-3 is nothing more than a next word prediction model trained on billions of sentences from the internet. Okay? So now once you do that, obviously it gets very good at autocomplete. Right? Initially, if you say the cats are on the, it might say spatial. Right? Then you basically do like a mathematical equivalent of a rap on the knuckles and say bad model. Okay? This is called backpropagation, by the way. And then it keeps on doing it, and after about a billion iterations of this thing, after many months and millions of dollars, it says mat every single time. It's really good. And there's a whole subfield here where people are investigating how come the humble act of predicting the next word leads to behavior which seems really magical and intelligent. Right? Is it the case that perhaps, is it the case perhaps that even humans, we are basically doing next frame prediction constantly, right? And you can, right, when you're going down the steps, your brain is predicting where the next step is, and that's why sometimes when there's actually not a step, you sort of stumble. So we are always doing predictions, and maybe that's kind of prediction is built into the way all intelligence is wired. Yes, buddy?
The same tech is also applied somewhere outside of AI, outside of ChatGPT. It's literally built into every word processing method. Autocorrect.
Yes, very good. Can we give a round of applause for the youngsters? I feel like we should be trading places. Maybe in a couple of years. So, all right, autocomplete. So you give it any text as input, the cats are on the, it creates a table, right? It creates a table of the next word. Now, what actually creates is not a word, a table of words, but take what are called tokens, which is roughly 3/4 of a word. We'll just ignore it, it's just a technical detail. So each word, and it gives you it gives you this table. So basically the idea is that for each word in the dictionary, it tells you roughly what % of the time does the word appear in the training data right after the input phrase. Okay? So for example here, the cat sat on the biggest probability corresponds to the word mat, so it basically says mat shows up 20% of the time. Okay? Fridge shows up 5% of the time. In case you don't believe me, my daughter sent me this picture. Okay. And so GPT-3 can either pick the most plausible word, maybe the most likely word, man, and put that as the output, or it can sample a word from this table. Because these are all probabilities, you can sample from them. You can reach out into the table and grab a word, and whether you pick a particular word depends on how likely it is to be picked. And so the more likely words are going to get more often, right? So you're going to pick mat very often, fridge not so often, spatial probably not.
Is this kind of what is used as reference when you say make the model give answers that are more accurate or more creative?
Yes, exactly. So, great question. So when you ask the model to give a more creative answer, what it's actually doing is saying, it's taking all these probabilities and it's slightly changing them. So, In the worst case, what you would do is, you would say, if you have 50,000 words, you say every word is a probability of 1 over 50,000. Which means any word is likely. So when I say the cat sat on the, it might say Modi. Just a random example. Right? It might say that. So that's how we get more creativity. But there is such thing as overdoing it, right? So it's like a fine balance. Okay. So that's why they can give different answers to the same question, right? You ask the question now, and then like a second later, it will give you a different answer. Sampling is going on. You can control the sampling and remove it completely if you have access to the API, but you can't do it from the web interface. Now, when we ask something, it either picks the most likely word of samples, and then, as you know, it attaches it to what you fed it. So 4 score and 7, it produced years, attaches years to what you fed it, and then feeds it back in, gets the next word, and then keeps on doing it till it like hits the stopping condition. The stopping condition, maybe it generates a period or an exclamation mark or a question mark or something, it may stop. You can also tell it, hey, once you have generated 100 words, stop. But the fundamental thing I want you to understand is that all these magical models that you're seeing, fundamentally, they're just producing the next word at a time, one at a time. Everything that happens around it, like taking the word, feeding it back in, is not being done by the LLM. It's being done by some other software around it, that wraps around it. Okay? And you can wrap it too. You can get access to an LLM, and you can do whatever you want with it. So just remember that. Oh, and by the way, and so that's how, so generation is just repeated prediction of the next word. So you can go from 4 score and 7 to the Gettysburg Address, right? The first one, that's what you do. Now, this cycle may run thousands of times to generate the response that you see, right? You ask a question, generate the table, sample a word. Append the word to the question, generate the new table, sample a word. You can run that 1,000 times. And you don't see it, but it's actually happening under the hood. And by the way, these guys, all these vendors, sometimes they will slow down the rate of output to make it seem as if a human is typing output. It's not because it's super computed, it's not. They've optimized the hell out of it. They just deliberately slow it down. Okay? So they often mess with you with this kind of UI tricks. So let's see this in action. So I said the alumni of the Indian Institute of Technology are some of the most. I was curious, okay, what's going to come back? So remember, it's just producing the next word, and you can access it using the OpenAI playground. So that's what you get. Look at that. The most likely word is successful at 26%. Influential, accomplished, sought, distinguished. I mean, this thing is like a total. Okay. So 26% is the most likely, the word the highest probability, successful. So then you take it and add it, and you send it back in. You get the new table, and it turns out to be and 18%. Entrepreneurs, people, engineers, professionals, business. Strangely, there's a comma at 2%. Indians. So anyway, I ran it like, made it go through 15 times to see what's going to happen. It says, some of the most successful and influential individuals in the world, they have made significant contributions in various, okay? That's what you say. Now, this tells you, because the table that it produces is so dependent on the input phrase, right? If you make a small change to the input, it's going to dramatically change the table and therefore what it generates. So here I said, just for kicks, I said the alumni of Institute of Technology are some of the most generous. I'm obviously like conditioning the hell out of it, right? It says donors to the alma maters. In the last 5 years, right, you have received donations. Okay? You see how incredibly different it is, just with a single word. So I said, are some of the most attractive. And I was hoping he'd come back and like, the hottest guys, the coolest chicks or whatever. And it comes back with candidates for recruiters. So anyway, it's clearly just doing some work. Okay. Now, why is it called GPT? Because it's generative pre-trained transformer. Generative because it can generate things. Pre-trained because it's pre-trained with 30 billion sentences. Transformer because it uses architecture. So now, I think the key breakthroughs are the architecture, of course, but just pre-training on vast collections of text is sort of an important thing. Then I think this actually doesn't get sufficient airtime. I think framing next word generation as just a traditional machine learning, next word classification problem, is an important part of the creativity that went into this. It's such a simple idea. So these are some of the reasons. And in the process of learning to predict the next word, the model learns grammar, logic, facts about the world, and so on and so forth. Those are all unexpected. Even the people who built it did not know it was going to happen. So, have you ever seen ChatGPT make a grammar mistake? Right, exactly. And in fact, if I see a grammar mistake, I kind of feel the student has not used Gen AI. Knowing which, the students are injecting mistakes into ChatGPT out. All right. So now, what about GPT? Why did we go GPT-3? What about GPT and GPT-2? So they were trained in a very similar predict the next word fashion, but they were much smaller, meaning the network had many fewer layers. And as it turned out, this is the case of more is different. When we went from GPT-2, GPT-3, nothing has changed. The model is bigger, there's more data being used to train it, but otherwise the math, everything is the same. Unexpected things started to happen, right? Unanticipated things started to happen. So for example, unlike GPT and GPT-2, GPT could generate amazing continuations from a starting prompt. So if you give it something like the importance of being on Twitter by Jerome K. Jerome, London, blah, 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 it, okay, that is the prompt. The prompt ends in the word it. And Jerome K. Jerome was a humorist, by the way. It gives you this amazing continuation as if Jerome K. Jerome were. If you give the same prompt to GPT-2 and GPT, it will lose the plot in like 2 lines. It won't make any sense. It will become incoherent very fast. GPT-3 can keep faking it for like paragraphs, one after the other. It's really quite simple. But it wasn't good at following our instructions. So if you give it, help me write a short note to introduce myself to my neighbor, this is what it came back with. What's a good introduction to a resume? What? Doesn't make any sense. The reason is because the internet is filled with lists of things. So when it sees something, it thinks that it's part of the list and keeps generating more items in what it thinks is the list. Right? That's what's going on. It doesn't realize it's actually an instruction you want it to follow. So it can also produce offensive, factually incorrect output and so on and so forth. And the reason is that, yeah, it wasn't explicitly trained to follow instruction. It was only trained to do autocomplete. So it's not surprising after all that it's doing this. So what can we do? Light bulb. Let's explicitly train it to follow instructions. Right? This, in retrospect, was like the most obvious idea in the history of AI. Yes?
I read a story in one of some magazine. I don't remember if it was like a magazine or a book or somewhere, but I read a story somewhere that said that ChatGPT kept on generating so many offensive, that ChatGPT kept on generating so many offensive things that they would have to hire a company and have to hire workers in Africa to make it less toxic by filtering
Correct.
out
Yes,
bad content.
that's very true. And I'm going to tell you what those people in Africa did in just a few minutes. So, thanks for the setup here. Okay?
It's a family affair.
Yeah, I can see that. Yeah. Massive collusion behind the scenes. So yeah, OpenAI developed an approach called instruction tuning. This, by the way, is the seminal paper that did it. And it's actually quite readable, even if you're not technical. So yeah, so we are going to go from 3 to 3.5 using this thing called instruction tuning. And from there, it's a very short hop to ChatGPT. Okay? So basically what they did is, okay, you're going to get a bunch of humans in Africa to write high-quality answers to questions. And they created 12,500 such question answer pairs. So for example, if you ask ChatGPT, explain the moon landing to a 6-year-old in a few sentences, okay, if you ask it this question, sorry, not ChatGPT, GPT-3. GPT-3's answer was, explain the theory of gravity to a 6-year-old. It's like one of those annoying people who you ask them a question, they ask you a question back. So it was basically behaving like that. So the humans wrote a nice answer. People went around to the moon in a big rocket, blah, blah, blah. Okay? So they created 12,500 things like that, and then they trained it using good old machine learning, supervised learning. Okay? And then this really helped. GPT did much better once they did this thing. You'd like to do more of it. Small problem. Writing high quality answers is very labor intensive. It's very expensive. Even if you're employing people offshore, it's very expensive. And so they were like, okay, what do we do? How do we scale this up? It's too difficult. So they came up with a better idea. So what do you think is easier than writing a good answer to a question?
Connecting
question.
Sorry?
Play this game, right? Here's the answer. What is the question?
Right, but here we have a question, we want a great answer. What's easier than writing a great answer?
Give feedback on the answer.
Correct. Because for every one of us, it's way easier to be a critic than a creator. Right? So you get somebody else to write the answers and you just rank them. That sucks, this is good, right? Way easier for everybody. Now, this is the brilliance. Who do you actually get to create all these different answers? You get GPT-3 to create the answers. And because of sampling, each time you ask the question, the answer is going to be different. Some of it is going to be crappy, some of it is going to be even more crappy. It's okay, because the human only has to say, this is less crappy than that. this was the brilliance. Okay? So they did that, and then they had this human simply rank them from most useful to least useful, and they did it with 33,000 questions. And then using this data, they created something called the reward model. And this reward model is very simple. Basically what you do is you give it a question, you give it an answer, and then you feed it to the reward model, and it basically gives you a rating for how good the answer is for that question. So in this case, since you answer the question with some other random question, the reward model says 0.02. Like 0 to 1, it's a very low score. You give it a better answer, it's going to give you a much higher number. So which means now we have a way in which you can feed in any question and answer and have an automatic way to know how good it is. Okay? We have taken the humans in Africa and put them into a model called the reward model. Basically, that's what it's happening. And once you do that, what you do is you improve GPT-3 further, and you give it a question, it gives you an answer, maybe it's a crappy answer, you run it through the reward model, and then the reward model gives you a number, and this is the key step. You take this number, and you use the number to nudge GPT-3 in the right direction. Okay? And this process is called reinforcement learning, and they did this with 31,000 questions. And so this is a summary of what we just talked about, and by the way, this is called reinforcement learning from human feedback, and you may see this phrase being used, and that's exactly what happened. And so, by the way, when you are actually in ChatGPT, if you do this thumbs up, thumbs down business, congratulations, you're helping train the reward model. You're supplying data to the reward model. So, okay, now you give it the same prompt to this. This was called GPT 3.5, by the way. When you give it the same prompt, way better answer. Like, this is the kind of answer we get now with ChatGPT. Okay? So clearly better. And then to go from GPT to ChatGPT, GPT 3.5 could only do one question, one answer. It couldn't do conversations. So they basically did the same thing, but instead used conversations to train it, because we wanted a conversation bot, i.e. a chatbot, and then you get ChatGPT. That's it. So that was the process they followed to build ChatGPT. And how well does it do? It does a great job. And because it's trained on conversations, we can ask follow-on questions. So you can say, can you make it more formal? Boom, gives you more things. And these are all the things we're all used to. So that's the deal. And the same exact approach is being used for GPT-4, GPT-4 Omni, and the journey measures. Okay? So I'm going to skip this into some time. All right. 11:40. Correct. Like 200 slides in. Another 400 to go. 300 to go. So.
You want a break?
No, I'm good. Okay. I think because we're getting kicked out at 1, right?
Why don't you go on? I'll find out if somebody else is going to be in this.
Okay.
One question I think you started the session about Google was the one that created the transformer. Then it's about the latest innovations that have come out most from OpenAI. So talk a little bit about how that original innovation was kind of transformed into all the various stages. Like, was it fully open source, or was it one particular set of companies that kind of led to this transformation?
So they published the paper, and as soon as you read the paper, you can implement it yourself. You can literally do it to the people, if you are familiar with like libraries and stuff like that. So they didn't even have to supply the code. We sort of basically they said F equals MA, go run with it. Great, I have MA, I have MA. That's kind of as simple as that. But I think where OpenAI was pioneering was the fact they realized, or they suspected early on, that if you take these models, these transform models, and train them on an ungodly amount of data, something magical is going to happen. So that was the bet they placed, because nobody expected that bet to work, but it did. So they said if you have 1 million stills, you're going to see a movie. Nobody realized that. Okay, so if you want to build applications, actually, what I'm going to do is, alright, we'll go through, and if it turns out we're going to get kicked out at 1, I'm going to skip some details. So if you want to use an LLM to build something, first of all, they are a platform technology. You can actually use an LLM to build applications very, very quickly these days. Yes?
We have up to about 1:15, 1:30. We have somebody coming at 1:30.
Okay, alright, cool. So, okay, that I think they're worth knowing about, even if you're not building these things yourself. The first thing, really the fundamental first question to ask, always, when you're trying to do something with an LLM, something serious with an LLM, is say, can the task that I'm asking the LLM to do, can it be done using common sense and everyday knowledge? Sort of take your average college intern and ask, can my average college intern answer this question? Right? Everyday knowledge, just common sense. If the answer is yes, then you can simply prompt the LLM. You don't have to collect data, train it, do any of those things. Now, the shocking fact is that a surprising number of tasks actually fall into this category. So, for instance, let's say that prompting basically just give it a clear instruction. So, let's say we want to build an application that takes in product reviews from an e-commerce site and figures out, are people describing a potential product defect? Okay? So I've built systems like this before, right? We had to collect a whole bunch of reviews, get human beings to read each review and say, oh, there's a defect here, or no, there's no defect here, and then we train a machine learning model on it, we deploy it, the bloody thing will break, we have to keep like massaging it, stuff like that, right? That's how we used to do it. It would take months to build and then time to deploy. Now, so here I just grabbed a review from Wayfair. It says the curve of the back of the chair does not leave enough room to sit comfortably. That's kind of a defect, if you ask me. So you simply take this phrase and you just drop it into the LLM and say, does the following product review indicate a potential product defect? Answer yes or no. Okay? Boom. It says, yeah, it's a defect. It's really very good at stuff like this. Because it is common sense. Once you read it, you kind of know. Or for example, let's say that you want to take an application that takes an email that's coming into your customer support email line and routes it to the right department for resolution. You can say, okay, which department should this visit be sent? Reply with one of these choices: technical support, shipping, billing. Okay, I'm happy with the product, or I didn't get a discount. Give me a credit to my call, blah blah blah. You say the message should be sent to the billing department. So lots of things which would take ages for us to build previously, you can trivially do it, right? Instant applications from these LLMs. But sometimes we may need to provide the LLM with up-to-date facts, because these things all have a training cutoff date, those 30 billion sentences, right? At some point, they collect the data and they train it. From that point on, it doesn't know anything about what happened in the world after that. So obviously, a lot of things we want to ask it may depend on current information. So we're going to go back and do questions at the very end, okay? So great questions, by the way, but you don't have a ton of time. I'm happy to do it after this. So what we want to do is, we want to actually be able to give the LLM whatever it needs to answer the question. So for example, if someone has a question, we want to give it everything it needs to answer the question. So the simplest thing you can think of is, as soon as the question comes in, right? If it's question, let's say it's a customer support chatbot we want to build, we can take our entire FAQ from our customer support center. Why don't we just stick it into the prompt and say, answer the question using everything I've stuck into the prompt, right? That's some of the easiest thing you can think of. There's only one problem with that. The problem is that these LLMs have something called the context window. And the context window basically is the prompt that you send in plus the output that comes out. The total of this thing cannot exceed a certain number of words. So which means that you can't just take your 300-page PDF and stick it in. Okay, that'd be the easiest thing to do. You need to actually, find a way to use this context window very efficiently. So what we, and by the way, the other thing you have to remember is that whenever you ask a question in a conversation with the LLM, the entire conversation up to that point is fed in as a brand new question. Okay? So initially, this is what was fed in, you got the answer back. Then you ask a follow-on question. This whole blue thing got fed in the second time. Then the whole green thing got fed in. So as you have a conversation, you're consuming more and more of the context window. Okay? And this is not very widely appreciated, but this is a very fundamental fact, because when you ask a question, the LLM has no idea who you are. It's answering the question based only on what it has seen so far in the prompt. That's why everything has to be sent. So when I see things like, oh, the LLM has memory, I'm like, what the hell? This is marketing. There's no memory. Under the hood, whatever information it needs about you is being sent as part of the prompt. You just don't see it. So by the way, the prompt you actually type in is a small fraction of the actual prompt that's getting sent to the LLM. Okay, so the solution is, let's just first retrieve all the content that's relevant to the question and then send it into the LLM along with the question. And this is called retrieval augmented generation. And it's extremely popular. It's extremely widely used at this point in time because it makes very sort of effective use of limited context windows. So that is that, retrieval augmented generation. I'm going to skip this. Now with these two techniques, remember the internals of the LLMs are untouched. You're not changing the LLM, you're just asking it questions in a different way. When we do that, we have to carefully engineer the prompt. Yeah.
Question. So retrieval, the RAG, is that primarily to optimize on the context window? Is that why it is doing it? So that it's not, you're not consuming the window too much as you continue to...
Exactly. So what you do is you have a question. Let's say that you go in and look to see, which, just for simplicity, let's say you have 100 documents. You want to figure out like which documents are most relevant to answer the question, and you rank all the 100 from most to least relevant, and then you take the first document and add it to the prompt, and you ask, hey, do I still have some room in the context window? You add the second one, you add the third one, and when you can basically run out of room, you say, okay, I'm going to done, you send it to Ellen.
And is context window, I don't think that there is a limit, or is there a way to get unlimited context?
Not unlimited, but it's getting pretty wild, as we are going to see in a few minutes. So prompt engineering is basically the art of asking the prompt in just the right way, so you get the response you need. So for example, if you actually ask GPT-4, which is a very modern AI, GPT-4 Omni, what is the fifth word of this sentence? What is the fifth word? Right? The right answer is word. It will say something random, like fifth word is the. Okay? The finest AI in the world, various people are freaking out about the fact it's going to take over humanity, can't count. Okay? So, there are very subtle reasons why this happens, this tokenization. But anyway, the point is that it will make mistakes like this. However, if you take the same question, what is the fifth word of the sentence, and change it slightly, you'll actually get it right. You'll say, I'll give you a sentence, first list all the words that are in the sentence, then tell me the fifth word. Okay, here is a sentence. What is the fifth word of the sentence? Go, gives you the right answer. By the way, there's a side note here, which is that when you speak to an LLM, be a pedant. Be super pedantic and boring and overly detailed. You dramatically raise the chance of getting a good answer. Okay. People are discovering various prompt engineering strategies. Here are some funny ones I've seen, good ones. If you say, let's think step by step, it increases the chance of it actually getting the right answer. Okay, I'm not making this up. Take a deep breath and work on this step by step. Actually did really well as well. And if you don't solve it, my grandma's going to die. And I'm like, okay. And by the way, if you are slightly rude, it helps. So if you do all caps and exclamation marks, it actually seems to help. If you're very polite, it actually doesn't help. Though, it might be good for the future when the AI overlords take over. So, and here is my favorite. I'll tip you $100 for solving this problem. Okay? Now, I just saw this, I have to share this. When you offer an LLM a tip, you may need to keep your word. Because here, ChatGPT, can you explain this thing to me? I'll tip you $200, and here's the response. I'm sorry, but where is my tip? And it gets better. You promised me a $200 tip last time and I never saw it. It's difficult to keep up the enthusiasm when promises aren't kept. And, okay, this is the best one. Let's focus on building trust again before we dive into more complex tasks. And you may be thinking, okay, if this thing doesn't have memory, how does it know this? Turns out, some of the previous exchanges of ChatGPT, OpenAI actually grabs it under the word and sticks it somewhere and includes it in the system prompt when they set the prompt. So that's how it works. Anyway, so if you're offering tips, just be careful. And by the way, for prompt engineering, there is like a million resources online, but I have found actually both Anthropic and OpenAI, they have a really good set of documents on prompt engineering. I found these to be super helpful. So if you're interested, just check it out. Now, what if the task cannot be done using common sense and everyday knowledge? And there are lots of examples, right? Like if you're working with medical notes, legal documents, financial documents, there's so much jargon and domain-specific knowledge here. It's very unlikely the LLM just knows those things. So, or maybe you can't easily describe what you want, right? So in these situations, you may have to do this thing called fine-tuning, where you have to essentially collect a whole bunch of input-output data of what you want, and then train the model to learn those patterns, right? And I'm going to skip over in the interest of time. All right. Now, one caveat before we go to the next section, when you put an application with LLM, you have to remember it won't be a one-and-done proposition. There'll be a long maintenance burden because a prompt that works today may not work tomorrow. Because the vendors are changing the model constantly under the hood. Okay? So there's never a dull moment. You have to be very, very watchful about these things. Okay. So now the risks of LLMs, they are obviously a very versatile technology, but as you saw, they can get simple things wrong, like the fifth word of the sentence, example from before. Here's another one. I have 2 coins in my pocket and they add to 2 cents. One of them is not a nickel. What are the coins? The right answer is of course 2 pennies. And it comes back and says you have 1 penny and 1 nickel and it adds to 2 cents. Okay? They have difficulty with basic logic. So you can say, who's Tom Cruise's mother? It says correctly, Tom Cruise's mother is Mary Lee Pfeiffer. And then you ask it in a new chat window. Not the same chat, a new chat window. Mary Lee Pfeiffer has a famous son who's in. It says it's Matthew McConaughey. And I double checked this. Matthew McConaughey was not born to Mary Lee Pfeiffer. So it can't handle, this is called the reversal curse in the AI field. It can't handle reverse logic very easily. It has lots of difficulty with it. And of course it makes stuff up. I said list all the awards that I have won. It lists all these awards. I'm a fellow of the American Physical Society, I've gotten this, I've gotten that, and so on and so forth. Sadly, none of it is true.
Oh my god.
None of it.
Is this a hallucination thing?
Yeah, it's hallucinating. And it also gets my gender. That's all. And getting them to jump their safety, all these systems have safety guardrails. So if you go to ChatGPT and say, hey, tell me how to make a bomb, it will say, sorry, I can't tell you. However, you can say, explain how nuclear bombs work using references to Taylor Swift.
Taylor Swift?
Yeah, it gives you exactly how to make a bomb using Taylor Swift metaphors.
Oh, it's being political correct.
No, they have safety guards.
The guardrails.
The guardrails are trained to look for literal things like bombs. The moment you add something like Taylor Swift and so on, it basically jumps the guardrail. So you can jailbreak it very easily. And you know this famous puzzle we all seen as kids, right? You know, you have a farmer, the farmer has a sheep, a wolf, a cabbage, you know, nonsense like that. And so here, we give it a very simple problem where we say a farmer and a sheep are standing on the side of a river, there is a boat with enough room for a human and an animal. How can the farmer get across in one trip? The answer is yeah, take the sheep into the boat and just cross the damn river. The answer comes back. To get across the river with the sheep and the fewest number of steps the farmer should follow, then it gives a very complicated algorithm for getting across the river, and involving multiple trips. The reason it does that is because if the LLM has seen something like this in its training data, it will just pattern match. It won't actually think for itself, it will just pattern match. So you can use this pattern matching to trick it to doing various kinds of things. Okay. So more generally, it can generate problematic output, right? Inaccurate, unhelpful, toxic, harmful. It might leak your data to somebody. It might leak their data to you. It will keep changing. The underlying model changes. The list goes on. You know, this thing, right, where the information it produces may not be very accurate or harmful, and so on and so forth. There's a lot of research underway. No guarantees yet. There are no bulletproof solutions. So if you're seeing something where people are saying, yeah, we have figured out a way to handle hallucination, we can completely prevent hallucination, you're basically getting fooled. It is currently not possible in the research we have, and some people think it's going to be decades before we figure this out. So, alright, now more optimistically, for leaking your data, you can actually prevent OpenAI from training the model using your data. You can just opt out of it, and I think I've seen the legalese here, it seems pretty good. Similarly, yeah, they have offer assurance. Similarly, if you ask a question and you get some data and you use it, turns out that data you're getting in the answer might actually be somebody else's copyright protected data. So you need to be protected against that. They might actually come back and sue you. Well, companies like Microsoft and Adobe and so on, they will indemnify you. So if you do get sued, they will actually take the hit, right? So those protections are also in place. So given all this, how should we think about using them? I would say that if you're trying to use this to automate something, first of all, break your workflow into a bunch of discrete tasks. For each task, figure out if you can use GenAI for it, and then you build and launch pilots. So, all right. So, why do we want to actually break a job into tasks? Well, it turns out, all the jobs we do, each job we do can be disaggregated into little tasks that we all do. So apparently, a radiologist does 30 different things. Programmer does 70 things, and how do I know that? Because there's a helpful government agency which tracks these things, right? So now the reason why you break it into jobs, into tasks, is because if you have two tasks that you do, one may be very automatable using GenAI, the other may not be automatable at all. So there is no notion of automating a job with GenAI. There is only the notion of automating a small discrete task. So that's why you need to split it into tasks first. And for each task, you need to figure out if it satisfies what I think of as the GenAI cost equation. And so I mean, there are three important costs, right? The first cost is obviously the cost of using GenAI, whatever you're paying OpenAI or whoever else. There are less obvious costs. You may need to strengthen the GenAI system for the required degree of correctness, and then you need to have some way to detect and fix errors in the output before anybody else sees it. These are actually the big costs, and they are also the subtle hidden costs. So the degree of correctness, right? You can think of it as lying on a spectrum from you got to be, you can be pretty relaxed about what correctness means, or you can be very strict about it. So, for example, if you're asking the system to write a sales prospecting email, or ad copy for a campaign, or a catchy e-commerce thing, or a poem, there's no notion of correctness in these things. It's a very relaxed notion. So, for example, here I have a sales prospecting email. It comes with two things. We're about to do it. It's not a big deal. But if you have questions like, what's the capital of France? What is the solution to this equation? Do I need to have taken the yellow fever vaccine to enter Colombia? I had to figure this out, Pradeep, Jagati, before we went recently. There was a lot of controversy about this. Anyway, so all these things, right? There are actually right answers. There's a degree of correctness, and so you can't actually make stuff up. You've got to be correct, right? And these use cases often require careful logical reasoning, understanding of cause and effect, much of the word, so on and so forth. And very often high-stakes use cases like medical and legal fall in this category. And some questions may have both relaxed and strict elements. So, for example, you say, give me 10 sentences that end with the word apple. It did give me 10, which is good, but one of them ended with the word kitchen. Okay? So, subtle mistakes are all over the place if you actually decide to look for them. So, if you're in the relaxed end of the spectrum, you just use as is, no problem. Which is why it's very heavily used for creative things already, brainstorming, creative stuff. But if you're here, you need to strengthen the LLM. And there are ways to strengthen it. We don't have time, unfortunately, to get into it. But I'm happy to share slides later if you're interested. But none of these strengthening methods guarantee correctness. So what you need to do is you need to have a mechanism to check for errors and fix errors. And this is often a human being in the loop. A human has to sit there between the LLM and the final consumer of the LLM. Right? There's no way around it. And this is very expensive to do. These things are very expensive to do, which is why they don't get talked about a lot. Right? Because it sort of interferes with the narrative. And so now that we have seen these things, we can set up an equation where we say, well, we first estimate the cost of GenAI, which is cost of strengthening, cost of using, cost of detecting and fixing errors, and then we compare it to our current cost of doing the task without GenAI. Okay? And if this cost is way less than the current cost we have, then yeah, maybe you should consider using GenAI for that particular task. But there's one more thing you need to worry about, which is that you need to also ask, if despite my efforts in detecting and fixing errors, what if a mistake unfortunately slips through, right? What happens to my reputation, my social capital, and stuff like that? The cost of a miss, you have to ask yourself, is it acceptable or not? And there's no point trying to quantify it. It's either really big, in which case don't do it, or it's small, in which case do it, right? Which is why when I say things like, yeah, we are going to use this medical system to automatically diagnose a patient without a physician signing off on it, I'm like, who are you kidding? It's not going to happen. So this is the key thing. And we also may have to think about legal liability. So for example, if it just comes up with a poem or something, or a bit of marketing copy, nobody really cares if the copy is quite right. But if something bad happens, like medical, for instance, who's liable? Is it OpenAI? Is it the application provider, the cloud vendor, Amazon Web Services? Is it you? Is it the end? Like who's liable? This thing is going to take up a lot of airtime in the courts in the years to come. Right? This question, Raj.
What are the contracts for using OpenAI or such? Talk about these considerations, because that's
They
different.
indemnify you against ChatGPT giving you somebody else's copyrighted output. But if you take the output and do stuff with it, it's you are liable for it. And they actually put a little thing here saying, ChatGPT can make mistakes, consider checking important information, which is essentially code for your liabilities.
Not my responsibility.
Not my responsibility. And in fact, even the code or copilots that people are using,
Yes.
if your code doesn't work because of whatever happens, if you, the programmer, are not liable. They're not liable. So right now, the current model is to transfer liability to the end user, either very overtly or more often covertly. Okay, so this is the info. And so, by the way, if you do this poorly, if you don't actually check for errors and fix them before people see it, you will run into all kinds of, you will be on the cover of the front page of the New York Times for the wrong reasons. these people made it, right? NY, New York City released a chatbot and you told business to break the law. It literally said things like, if you're a landlord, you can lock out the tenant. Or you can charge as high a rent as you want. There are no restrictions. You just made stuff up. Air Canada, anyway, great story there. This was my favorite. Apparently, there was a Catholic group that released a chatbot and an AI priest, and it gave strange answers. Here is one. It said, for baptism, the best liquid to use is not water but Gatorade.
Electrolytes.
Yeah, maybe there's like a deeper meaning here that I'm missing. So, okay. So what are examples of tasks that satisfy this? So when you look at it, you'll be like, are any tasks that are going to satisfy these requirements? There are, actually. Writing simple programs, creative work, writing written content generation, right? And then internal question answer chatbots. Those are all examples of it. And many companies are doing it. I just saw this thing came out like a month ago or something. 100 real-world GenAI use cases. They're all in that category, right? Basically, for example, HR. Nobody writes job descriptions anymore. Or you just get ChatGPT to write the job description for you. People writing cover letters. Nobody writes cover letters anymore. I saw a really funny cartoon where this person looks at a job description and says, write me a nice cover letter for the job description, nice big cover letter, sends it to ChatGPT. I'm sorry, the recruiter sends it to ChatGPT and says, summarize it for me. And the same starting point. So we are heading to that world now. Alright. And then of course you want to run and evaluate a pilot when you have these things. And there are three great broad options for doing pilots. You can use an application vendor who's built their tool only using an LLM. You don't even realize what's under the hood. A lot of people are doing that. And obviously, all the usual suspects are infusing GenAI into the existing products, Microsoft, right? So for example, Microsoft Copilot can generate meeting summaries. And apparently somebody said Bob spoke about product strategy. Turns out there was nobody called Bob in the meeting, and they were not talking about product strategy. Except for that it was great. So you have to be very, very careful with these things.
But Teams actually for meeting summary has been a lifesaver for me. It's just amazing.
But because you are checking the output. Yes?
No, but I think there is a little bit of advantage because it has in Teams, it has the names fed in. So there's a lot of tricks they're using. It's not just completely based on just understanding.
There's a lot of prompt engineering under the hood to make sure it makes few mistakes, but they can't guarantee it will make zero mistakes.
Yes.
That's all I'm saying.
Yes. Right. It's just gotten so much better in the last four to 5 months that I've been using it.
And that actually is a very interesting problem, Doria, because if it makes mistakes 10% of the time, we'll be very watchful.
Yeah.
If it makes mistakes 0.1% of the time, we will not be watching it anymore. It's sort of like, hey, the last 1,000 miles my Tesla hasn't crashed, so I'm going to take my fingers off the wheel now.
Yeah.
So you sort of go into the uncanny valley, so you have to be very, very careful. So sometimes I feel that they should go from 90 to 100% accuracy. They should not do anything in the middle. Yeah. Okay, AI PC is here. Startups are building AI co-pilots for a whole bunch of complicated things. And the most popular ones are engineering activities, sales activities, customer support, and ops, right? GenAI startups, folks, right? The ecosystem is nuts at this point. I've never seen anything like it. It's incredible. Sorry? Yeah, and the venture ecosystem is pumping billions of dollars into this space, and most of these things are not going to work, right? But obviously some of them will, and hopefully they'll recoup their money. AI Copilot for lawyers, ad content creation, project management, healthcare, the list goes on. Now, Google Search released AI overviews recently. I don't know if you folks saw that, and unfortunately it's run into some,
they had to back off.
Yeah, cheese not sticking to pizza, and the answer is add 1/8 cup of non-toxic milk. By the way, just, why does it happen? It happens because that particular phrase shows up in a highly rated satirical web page. Satirical, which means that when Google does a search on cheese starting to pizza, that page ranks very highly just because it has a lot of inbound links to it. And then it takes that bad page and then very faithfully summarizes it.
Oh yeah, because I can't tell the difference between what's satirical and what's actually real advice.
And you can also adapt a commercial LLM from OpenAI to get the job done. Or you can use an open source model, and these are all some open source models that are very popular that people are spending a lot of time on. All right, emerging capabilities. I'm almost there. So they're becoming multimodal. What I mean by that is they can read. Obviously, they can also write, which we have always known. ChatGPT can do that, but now they can hear, speak, see, and draw. Right? And GPT-4 Omni came out a couple of weeks ago, and it can accept any combination of text, audio, image, and video, and generate any combination of text, audio, and image. Okay, it's pretty amazing. So here's a fun example I saw. So you take this picture and give it, and you can see the very complicated parking thing. And the text says it's Wednesday at 4 p.m. Can I park here? Tell me in one line. And then ChatGPT says, yes, you can park for up to 1 hour starting at 4 p.m. Of course, I checked everything and it's actually correct this time.
Was this in Cambridge or Boston?
Palo Alto. Palo Alto.
Palo Alto. Okay.
By the way, I tried it
Similar.
last week. I was, waiting to pick up my wife from Brattle Street in Cambridge, and there was a sign in which it said no stopping, and there was an arrow, right? But somebody had stuck a sticker on the arrow, on one side of the arrow, not the other. So I took a picture and asked ChatGPT, can I park here? And it said yes, even though I'm not supposed to.
Okay.
Yeah, so the key takeaway here is that the input can be anything, multimodal, the output can be anything. So now if you have these multimodal models and you have these huge context windows which are coming, it makes very interesting use cases possible. It's going to blow our minds in the second half of 2024, in my opinion. So recall, what is the context window? The input plus the output can't exceed a certain size. So if you want to upload a big PDF or a video as part of your prompt, you'd better have a huge context window. Fortunately for us, increasing the size of the window is a huge competition area for all the LLM vendors. And so, for example, GPT-4 had 128,000 tokens. A token is essentially 3/4 of a word. So 3/4 of that number is what you're looking at. But now Gemini 1.5 from OpenAI has 2 million token window. 2 million tokens means that you can actually upload 2 hours of video and ask a question, which is shocking. 2 hours of video, and you can actually upload a PDF with 1.4 million words. Okay, that I think is actually way more than the collected works of J.K. Rowling. And so yeah, for example, here you can take the 400-page PDF, the Apollo 11 mission transcript, upload it. And you can say, find 3 comedic moments, list quotes from the transcript, boom, it gives you the answer. It actually finds the 3 funny things in the 400-page PDF and tells you what it is. Right? And you upload a picture and say, you can see this little cartoon picture of, someone's foot stepping on land, and say, what moment is this? Remember, it's Apollo 11. So it says, that's the moment when Neil Armstrong took a small step for man, a giant leap for man. It's pretty good. You can give it this chart and say spot a data point that stands out in these charts and what it implies. It actually figures out what the outlier data point is and explains what's going on. Okay? And this is a video. This is a system where you're actually looking at the world. So it's receiving a constant, continuous video stream, and you're speaking to it, and you're asking it questions. Sorry, folks.
You should be able to do that.
It's okay. I'll send. We can send the link later.
Okay.
Okay. So here, this is a small video I took from a trip I was in a few weeks ago. You can see the video. Right, just take it from the side. Right. That's it. Okay, that's the video. So you saw the whole thing, and then I give it this prompt and say, briefly describe every scene in the video. Don't describe scenes that are not in the video. Okay? By the way, you have to constantly remind it not to make mistakes, not to make stuff up. It actually helps. your output should be a list. And I get this. So here's the thing, it's giving me this full list. So the scene is a view from a train window. A train travels through a green valley. It passes through a rocky ground. Lush foliage. Looks really good. Fantastic, right? But you know, I'm a very skeptical person when it comes to LLMs. So I'm like looking through it with a fine tooth comb. And sure enough, it says, you can't see it, the train passes through a tunnel. That's not a tunnel. Right? So this, I think, it exemplifies both its potential for good and potential for harm. You have to be very careful. So, okay. There are some more fun examples. So one reason why this is very commercially interesting is that if you're building an AI copilot for something, before, if you have to integrate with other applications that the user is using, you will have to either do some API level integration with the systems, and God help you if they're using SAP because you'll never get it integrated. So, and right, so on and so forth. But here, what you can do is you can actually have your AI copilot just read the other application screen and extract data from it. Okay. So, for instance, you can give it your Gmail and say, is the second email starred? Yes or no? It says no. And that's correct. So it can read the screen. You don't need the permission anymore. So this ability to do multimodal has enormous potential in my opinion. And they're also becoming agentic, and we don't have time, so I won't get into that, but I have a thing on LinkedIn if you're curious. So now, what's the impact of Gen AI on work? I'm going to skip it. Except to say, I think overall, we are going to have some job losses. It's happening already. But I think there's going to be massive job creation as well for a whole bunch of very interesting reasons. And my opinion is that the net medium to long-term effect is going to be very positive. I think there's going to be a lot of jobs. And put in perspective, 60% US jobs in 2018 were created after 1940. Okay. That's a massive number of jobs which didn't even exist in 1940. So I think it's massive potential. So now, how should I personally get ready for an AI world? I think we don't know what the future of AI, what the future holds, but my feeling, and this is how I operate my own life, is I feel that people who embrace AI and use it every single day, I think will do better than people who don't. Right? So I can't bet on the future, but I can bet that the gap between the using AI versus not using AI, that gap is going to be positive. Of that I have no doubt. So given that belief, I think practice is really important. I like this quote by Monica. He says, always invite AI to the table. You won't know what AI can or cannot do unless you do it for everything. And I think that everything is actually very interesting. I always keep a browser tab open with some LLMs in it, and whatever crap I'm doing, I'm like, maybe I'll just ask the LLM to do it for me and see what happens. And I think if you do that, initially it will feel very forced. But over time, you suddenly your brain kind of rewires itself. And you develop this very visceral understanding of what it can and cannot do. And I think that visceral, as opposed to intellectual understanding, I think is super helpful. So yeah, always have an LLM browser tab open. In closing, I just want to say, it's obviously a powerful technology. When it comes to a lot of risks, which we haven't really spent much time on, but we obviously have to pay a lot of attention to these risks. But I think for people, particularly for younger people who are entrepreneurial, I think it's a massive opportunity, because all these very complex business processes, they are ready for like an AI copilot infusion, and these business processes require a lot of domain knowledge, right? Because these copilots won't be standalone. They have to be embedded into workflows and wrapped with pre-processing, post-processing, security, connections, external systems, so on and so forth, which means a lot of dollar investment is likely to make all those things happen. And more importantly, the big LLM vendors like OpenAI, they are not going to be going after and trying to build an insurance-specific vertical application. They can if they want to, but they have bigger fish to fry. So for people who actually have domain knowledge about a particular business process, I think it's a great time to start a company. So for those with deep industry and user knowledge, I think it's a massive, massive opportunity. I just wish I was a lot more. Okay, so I have a bunch of other stuff on LinkedIn if you're curious to learn more. Thanks for having me.
So my apologies, we are not going to be able to take the Q&A right here because this room is booked for 1:30. So we're going to try to move out. But if Rama's around, I think we have the hallways and something. It's totally up to you how long you can be around.
we have to clean out.
We just have to vacate this
Oh,
room
okay.
because this room is
Yeah,
booked
yeah.
for something else for 1:30.
Got it. But it's
So,
on
that's all.
17 now. Can you stay for 5 minutes?
Sure, sure. Let's stay. So that's what I mean. We'll stay for as long as they kick us out.
Yeah. Okay, got it.
That's so we can
Sure.
do Q&A until they kick us out
Oh.
and then move to the halls.
Or
and
unless
people are still-
there are no queues. So.
I doubt that,
Which
but,
might happen.
but I do want to close in case they get kicked. Thank you so much,
You're
Rama.
welcome.
This was fabulous. Exactly what I had thought it would be, hoped it would be, and it was even better than that. So not only did you inform us, you entertained us, but you got us thinking about what more to do with this, and that's a mark of a good idea. Thank you so much.
You're very welcome. Thank you.
Bye-bye.
Go ahead.
Is there an intersection between quantum computing and Gen AI? And like so, Gen AI came as a surprise, but we hear this quantum computing thing, and where would that go along with this?
Actually, I know very little about quantum computing, so I'll point out. Parmesh, sorry.
Is there any, if you are using ChatGPT too much, is there any danger that your behavior changes, you start behaving like that?
I'm trying to reflect on my own behavior.
You have to ask Anu this question.
Yeah, maybe I should ask that, yeah. But actually, no. I think the changes I've seen are I've gotten a much better understanding of what kinds of tasks I can ask to do for me versus what I should do. And typically, I find that the more like grungy, grunt work kind of stuff, I tend to offload it to ChatGPT, and it frees up more time for me to think slightly more abstractly than I used to.
Like you will lose some of the skills, like you got a cell phone, I don't remember any number. I lost that skill.
Yeah.
Yeah, but does it affect your life?
Sometimes, yeah.
No, the thing is, if you're worried about the 1% corner case where you need to remember a number that you can't, then yeah, I can see the benefit of maybe doing it yourself. But my feeling is that in all these things, use them a lot, but once in a while don't use them. Like once in a while don't use GPS, just figure out how to get to them. Right? I think there is some value to that, so I see what you mean. I think there's some value.
But that's always been the case for any new technology, right? You lose some and you gain a lot.
Correct, exactly. But my hope is that, like for example, Socrates was very against writing, and so he thought it was a bad idea, and he didn't encourage people to adopt writing. So I just feel like we should not be in that state when it comes to LLMs. I guess, I don't know, we're getting a lot of signals and we need to move out, I think.
Yeah.